Hello friends, welcome to this lecture. So, in this lecture we will focus our study on nonlinear system. Before this we have discussed the phase portrait for the linear system and the types of critical point for the linear and weakly nonlinear system, and here we consider the kind of a general nonlinear system here. So, here in this case we have the Poincare-Bendixson theorem, which will discuss the behavior of the critical point of 0 comma 0. So, the solution and orbits of nonlinear equation studied earlier almost agreed with the corresponding linear equations. So, but in general it may not be true. So, first we start this discussion with the help of one example, and then we summarize the finding of the example as a theorem which is given as Poincare-Bendixson theorem. So, first let us consider an example and then we try to state what we mean by Poincare-Bendixson theorem. So, first let us take one example, dx by dt equal to minus y plus x into 1 minus x square minus y square, and dy by dt equal to x plus y 1 minus x square minus y square. So, here if we try to find out the behavior of the critical point, then you of course 0 comma 0 is a critical point here, and we can find out the orbit also. But let us simplify this equation by introducing the polar coordinate system, and if we introduce the polar coordinate system, so it means that x equal to r cos theta and y equal to r sin theta, or I can simply write that r equal to x square plus y square square root of this, and theta is equal to tan inverse y by x. So, this is the say change of coordinate from xy to polar to Cartesian and Cartesian to polar here. So, introducing polar coordinate system, we claim that your equations given in 23 may be written as dr by dt equal to r into 1 minus r square and d theta by dt equal to 1. So, let us spend some time on this. So, here we need to find out dr by dt. So, if you look at r square is equal to x square plus y square, let me do it here. So, it is r square equal to x square plus y square and tan theta equal to y by x here. So, if you look at 2r r dash equal to say 2x x dash plus 2y y dash, here dash represent the derivative with respect to t here. So, 2 will be cancelled out. So, it is r into r dash equal to x x dash plus y y dash here. Now, x dash we have already find out, x dash is equal to minus y plus x. So, it is minus y plus x 1 minus x square minus y square plus y y dash will be what? It is x plus y. So, it is x plus y 1 minus x square minus y square here. So, we can simply write this as minus xy plus x square 1 minus x square minus y square plus yx plus y square 1 minus x square minus y square, and this will be cancelled out, and what you will left is x square into this plus y into square into this. So, we can take out this 1 minus x square minus y square common, and what is left here is x square plus y square. So, it is nothing but r of r dash. Now, if you look at this is nothing but r square. So, we can simply say r dash equal to r square 1 minus x square minus y square. So, we can simply write r dash equal to r into 1 minus r square. That is what we have claimed here, that dr by dt equal to r into 1 minus r square. Now, for the d theta by dt, let us consider this also. So, d theta by dt, if you differentiate this tan theta equal to y by x, it is sec square theta theta dash equal to, here we simply say it is x square x y dash minus y of x dash. So, now sec square theta is 1 plus tan square theta. So, we can say 1 plus say y square upon x square theta dash equal to x. Y dash is basically what? It is this. So, x plus y 1 minus x square minus y square minus y of x dash, that is minus of y plus x 1 minus x square minus y square divided by x square. So, we can simply say that here if we simplify it is x square plus y square divided by x square theta dash is equal to, if you simply say that it is x square plus x y 1 minus x square minus y square plus y square minus x y 1 minus x square minus y square divided by x square. So, these two will cancel out and what you get is theta dash equal to x square plus y square upon x square, and if you divide it by this then it is same x square plus y square upon x square. So, here we can simply divide and we can simply say theta dash equal to 1 here. So, that is what we have written here, that by introducing polar coordinate we can rewrite the equation number 23 as follows: dr by dt equal to r into 1 minus r square and d theta by dt equal to 1 here. So, this d theta by dt just give you the direction, because here we can simply say that behavior maybe this orbit will be something like that, and this d theta by dt will just give you the behavior of the orientation, that orientation is clockwise or anti-clockwise, right. So, this d theta by dt is just give you the direction of the say orientation of the orbit here, the solution is moving clockwise or anti-clockwise. For example, here d theta by dt is equal to 1, which is a positive thing. So, it means that it is moving in positive direction. Now, what is your positive direction? It is anti-clockwise direction. So, it means that your that solution will move in anti-clockwise direction here. Now, first let us find out the general solution of equation number 24. Now, the reason here that we can solve this equation number 24 in a very easy manner, that dr by dt equal to r into 1 minus r square, it is quite in separable form, but if you look at the equation number 23, it is quite difficult to solve in Cartesian coordinate system. So, that is one of the very important benefit of introducing the polar coordinate system. Now, let us solve this equation in polar coordinate. So, we have dr by dt equal to r into 1 minus r square. So, we can write this as r into 1 minus r into 1 plus r here. So, we can simply say that it is dr divided by r minus 1 r plus 1 equal to minus of dt here. So, we just multiply by that. Now, we can use here the partial fraction and we can simply say that it is a by r plus b by r minus 1 plus c by r plus 1 dr equal to minus of dt. We need to find out the values of a, b and c. So, I can simply give you the values, but if you want to verify you can simply say these two are same. So, it means that a times r square minus 1 plus b times r into r plus 1 plus c times r into r minus 1 is equal to 1, and this is true for all values of r. So, in particular by giving different values of r you can find out the values of a, b, c. This is nothing but the method which we have generally used for in integration kind of thing. So, here we can put r equal to 0 and we can get the value of a equal to minus 1, and we can put r equal to 1 here and we can get the value of b as 1 by 2. Similarly, r equal to minus 1 we can get the value c as 1 by 2. So, we can rewrite this as minus 1 upon r plus 1 upon 2 of 1 upon r minus 1 plus 1 upon r plus 1. You can verify that it is actually coming out to the earlier one. So, minus of d of dt. So, we can simplify it is minus ln of r. Now, here r is basically x square plus y square under root. Here we are taking that since r represent the distance it is never negative. So, r is a positive quantity. Okay, so, minus ln of r plus 1 upon 2 ln of r minus 1 and plus 1 upon 2 ln of r plus 1 equal to minus of dt. Minus of t here plus some integration constant, let us call this as c. So, here I can simplify, I can simply write ln of r square minus 1 under root divided by r equal to minus t plus ln c. So, we can simply write this as r square minus 1 upon r equal to this e to the power minus t, you write it. Now this c I have already used, so let us use some other notation, let us say c1. So under root r square minus 1 upon r is equal to c1 e to the power minus t. Now let us square it out, and we have r square minus 1 upon r square equal to c1 square e to the power minus 2t. So we can simplify it as 1 minus 1 upon r square equal to c1 square e to the power minus 2t. So 1 by r square you can find out as 1 minus c1 square e to the power minus 2t. So r square is nothing but under root 1 upon under root 1 minus c1 square e to the power minus 2t. Now we have to fix the value of c1. So if I assume that r of 0 equal to say r naught, then we can find out the value of c1 here itself. So here your c1 square is basically as what, r naught square minus 1 upon r naught square. So that is this value. So here if you put the value r is this is r here. So here it is r. So this is r. So r equal to 1 upon under root 1 minus c1 square is this. So r naught square minus 1 upon r naught square e to the power minus 2t here. So this we can rewrite this as r naught square divided by r naught square minus r naught square minus 1 e to the power minus 2t here, that is your r here. Okay, so that is your c1 square value, is it okay? So that is what we have written here, that the general solution is given by RT is equal to R naught divided by R naught square plus 1 minus R naught square exponential of minus 2t. If you look at here, this is what we have written, minus if you take out, then it is 1 minus R square e to the power minus 2t here, and corresponding to d theta by dt equal to 1. So it is nothing but theta equal to t plus c. Now c you can find out by putting theta 0 equal to theta naught. So we can write down this as theta equal to t plus theta naught. So the general solution of this 24 in fact particular solution satisfying the condition r naught equal to r0 and theta naught equal to theta 0 is given by rt equal to r naught under root 1 r naught square plus 1 minus r naught square exponential of minus 2t and theta equal to t plus theta naught. So this is the say solution. So it means that now we can write down the solution xt as r naught divided by r naught square plus 1 minus r naught square exponential of minus 2t cos of t plus theta naught and yd as r naught upon under root r naught square plus 1 minus r naught square e to the power minus 2t sin of t plus theta naught. So here the solution of the equation number 23, differential equation number 23, though it is very difficult here how to solve this equation, but here with the help of polar coordinate system we are able to find out the solution given as xt and yt here. Now once we have a solution then it means that we can draw the orbit also and then we conclude something. Now here we simply say that if we take r naught equal to 1, that initial condition, if we take the initial point lying on the circle x square plus y square equal to 1, r naught equal to 1 means that x naught square plus y naught square equal to 1. So in that case your xt is equal to cos of t plus theta naught and yt equal to sin of t plus theta naught. So it means that if the initial point lie on the circle, unit circle, then the solution will always lie on the circle itself. So it means that your circle is like this. So if your initial point is somewhere here, then future point also it will remain here, because x square plus y square we can always get as 1 here. So it means that one of the orbit is given as the unit circle here, right. Now if we take r naught equal to not equal to 1 means either r naught is less than 1 or r naught is bigger than 1, then what is the behavior of the orbit. So we say that if r naught is not equal to 1, all the orbits of 23 except origin spiral into unit circle as t approaches infinity, that we wanted to know. So if I let us start with say r naught bigger than this, right. So if r naught is bigger than 1, then what we will have, if you look at x of t here, x of t is given by this, or let us more clearly it will be given by this here. So, let me look at here r t equal to r naught upon under root r naught square plus 1 minus r naught exponential of minus of 2 t, that is the behavior of r t. And this equation number 24 give you dr by dt equal to r into 1 minus r square here. So, this will give you, let me look at here, this dr by dt equal to r into 1 minus r square will give you the change of radius vector with the as t tending to infinity. So, if r is say greater than 1, then r square is certainly bigger than 1. So, this quantity dr by dt is negative, right. So, it means that your radius will be a decreasing function as t increases. So, as t increases, your radius will try to come down to say decrease. Now, up to what it will decrease? So, it means that here it is this thing. So, it means that here it will try to decrease, and ultimately it will try to come to this unit circle x square plus y square equal to 1, because as far r is greater than 1, it will dr by dt is always decreasing, but as r equal to 1, it means as it is touching the orbit x square plus y square equal to 1, it means that r equal to 1, then dr by dt is equal to 0. So, it means that then radius vector will not change. So, it means that as your this solution which is starting from say somewhere outside the circle, then it will try to, as t tending to infinity, it will try to come to near to your x square plus y square equal to 1, and as soon as it touches the unit circle, then dr by dt is equal to 0. It means that radius will keep on be constant. So, it will not change. So, it means that if we take any point outside and a solution passing through this, then it will spirally approach to the circle x square plus y square equal to 1. Similarly, if I look at the value r less than 1, right, then your dr by dt is now positive, because this 1 minus r square is positive and r is also positive. So, dr by dt is now positive. So, it means that radius vector is increasing function of time t. So, it means that if we take any solution somewhere here, then your radius will keep on increasing, right. And if you look at x t and y t, these are say periodic functions. So, I can look at like this. So, x t equal to this r t cos of t plus theta naught. So, if I look at t plus some 2 pi, then x of t plus 2 pi will be what? It will be like, let me look at here. So, here your radius is increasing and it is a periodic function. So, it means that it will spirally increase. So, it means that it will go like this and ultimately it will move away from origin, and at as soon as it will. So, now if we take say r less than 1, or say r of t is less than 1. So, it means that if at any time, let us say t naught, r of t naught is less than 1, then at this particular point dr by dt will be what? This is less than 1 but positive, it is positive here. So, dr by dt at t naught is positive. So, it means that for t greater than t naught, your radius vector will increase, right. So, it is, and for any time where r of t is less than 1, then dr by dt is always positive. So, it means that it keep on increasing for all values of t for which r of t is less than 1 till it touches the unit circle x square plus y square equal to 1, where your r will become 1. So, at as soon as your r will become 1, then dr by dt is equal to 0. So, it means that once this solution's orbit is approaching towards the circle x square plus y is equal to 1, and as soon as it touches the circle of radius 1, then your radius vector will be a constant. So, dr by dt is equal to 0. So, it means that radius vector will not change further. So, it means that it will always be on the unit circle. So, it means that the solution which started somewhere inside the unit circle will ultimately approach spirally towards the unit circle r equal to 1 here. Spirally because your x t and y t are periodic function of time t with increasing radius. If you look at x t and y t, these are periodic function that is very clear from this, and you can see that the radius means x square plus y square is keep on increasing. So, here let me write it here in this thing, that this is a unit circle here. So, if I take any solution here, then it will move it something like this, and as soon as it will be here, it will dr by dt will be constant, and it will remove, it will always be on this unit circle only. Similarly, if we take any point outside, then your radius vector keep on decreasing and it will come out to be the unit circle here, right. So, here as soon as it touches the unit circle, your dr by dt is a constant, and solution for future time it will always remain on the unit circle. So, this is very unique feature in the nonlinear system here. So, here what we have observed here, that the solution x t and y t is a periodic solution with period 2 pi, and this period for r not equal to 1, the solution is periodic solution with period 2 pi, and all other solution for which r naught is not equal to 1, all the orbits of 23 except origin spiral into the unit circle as t approaches infinity, that we have just pointed out, and that you can look at from this also. If you look at here, r t equal to r naught upon r naught square plus 1 minus r naught square exponential of minus 2 t. So, as t tending to infinity, this term will tend to 0. So, it means that r t will be what, r naught upon under root r naught square, it means that it is r t is equal to 1 only. So, the limiting behavior as t tending to infinity, r t will reach to r t equal to 1 only. So, that is clear from this also. Now, the system of equation 23 shows that the orbit of a nonlinear systems of equation may spiral into a simple closed curve. So, circle x square plus y square equal to 1 is a simple closed curve, right, which will represent the or one orbit, and all other orbits are say ultimately reaching or converging towards this unit cycle, and it is not possible for linear system. In linear system, this kind of things will never happen. So, there we have already seen that none of the orbits are intersecting each other, okay, and hence we in linear system this one circle one orbit is not spiraling into the other orbit. So, this is a unique feature in a non-linear systems. Also, without solving the nonlinear system of equation explicitly, it is often possible to prove that the orbit of a nonlinear system of equation spiral into a closed curve. Now, here whatever we have concluded in this example, this conclusion we obtained from the equation and solution of the differential equation. Basically, we have solved the differential equation and we are able to conclude whatever we are saying. But is there any possible that without solving the differential equation can we conclude something like this? Now, please, if you look at here, the closed curve is corresponding to a periodic solution. So, it means that we can consider the conclusion whatever we have concluded is to find out a periodic solution, that is there a periodic solution possible for a given system of linear equation. So, we can look at this observation in a different manner and to find out a non-trivial periodic solution of the corresponding nonlinear system. Now, here we try to state Poincare-Bendixson theorem to find out the existence of this kind of a phenomena without solving the nonlinear system here. So, here the Poincare-Bendixson theorem, which says that suppose that a solution x equal to x t, y equal to y t of the system of differential equation dx by dt equal to f x y, dy by dt equal to g x y remains in a bounded region of the plane which contains no equilibrium points of the 25, then its orbit must spiral into a simple closed curve. Now, that simple closed curve is itself the orbit of a periodic solution of 25. So, that will give you the existence of periodic solution as well as the extra phenomena that orbits of these solutions must spiral into a simple closed curve, okay, which correspond to a periodic solution of 25. So, by this we can also ensure that if this thing is happening, that orbit must spiral into a simple closed curve, and that simple closed curve is corresponding to a periodic solution. If you look at the previous example here, your solution is remains bounded in a region bounded by x square plus y square is less than 1 and greater than 0. So, it means that your solution bounded in a region given as annulus of x square plus y square bigger than 0 and less than 1, then the solution orbit which is starting inside that must say spiral into a solution that is x square plus y square equal to 1, the orbit of this x t and y t, which is corresponding to a solution of periodic solution. With this orbit x square plus y square is equal to 1 is corresponding to a periodic solution that we have just given here. Now, let us take I am not giving the proof of this Poincare-Bendixson theorem, which is little bit involving, rather than we are discussing some very good example based on this Poincare-Bendixson theorem. So, one example is that prove that the second order differential equation z double dash plus z square plus 2 z square minus 2 z dash square minus 1 z dash plus z equal to 0 has a non-trivial periodic solution here. So, first of all look at this is a nonlinear differential equation, and the corresponding system of two first order equation is dx by dt equal to y and dy by dt equal to minus x plus 1 minus x square minus 2y square upon into y. Now, here regarding this the non-trivial periodic solution, we have also discussed this problem earlier also. There what we have this thing, we just convert into system of two first order equation like this, and then we try to find out the orbit here dy by dx equal to this thing minus x plus 1 minus x square minus 2y square y upon y here, right. And if this orbit is coming out to be a closed curve and it will not contain any say equilibrium thing, then this will correspond to a this orbit is correspond to a non-trivial periodic solution. But it is provided that this dy by dx equal to this, it is a system of first order differential equation, nonlinear first order equation differential equation is solvable. If soluble means soluble in explicit manner, if you are not able to find out the equation of orbit, we cannot check whether it is a closed orbit or a just an orbit. So, here it is quite difficult when this is a general nonlinear system. So, here in this kind of problem we can use Poincare-Bendixson theorem to find out the existence of nonlinear non-trivial periodic solution here. So, now we try to find out a reason. Now, we want to apply the Poincare-Bendixson theorem, and for which we have to find out a reason in which your solution will remain bounded. So, let us find out the reason R in xy plane containing no fixed point and having the property that every solution of 27 starting inside that region at some time say t equal to t naught will always remain therefore all the time. So, we take R as annulus region about the origin. So, for that we simply look at this d by dt of x square plus y square upon 2 equal to x dx by dt plus y dy by dt equal to 1 minus x square minus 2 y square into y square. So, this you can find out, x dash is given by y and y dash is given by this, you can simplify and you can get it. So, to find out region R where your solution will always remain there, it is always advisable to find out dr by dt. So, by which we can simply say that by looking at this R, we can conclude something, that in region R your solution will remain there or not. So, this is a common practice to find out dr by dt, or if it is not possible, then you have to do something to conclude that in your region R your solution will always there. If it is starting inside the annulus in that region, it will always remain there having no critical point. So, region must be free from critical point, means fixed point and solution will remain there for that. Then we can apply Poincare-Bendixson theorem to say that the solution will spiral in a closed orbit, and that this theorem does not tell you anything about the closed orbit, that which one is your closed orbit. It just simply tell you that they exist a closed orbit on which all the solution are spiraling into it as t tending to infinity or t tending to minus infinity, and that existence of closed orbit gives you the existence of periodic solution of the nonlinear system. Okay. So, we are doing this, we are finding the region R. So, dr by dt of x square plus y square is coming out to be 1 minus x square minus 2 y square upon into y square. Now, with the help of this we will try to find out the region here. Now, look at that, y square is always positive, right. So, now everything will depend on this 1 minus x square minus 2 y square. So, I can write 1 minus x square minus 2 y square into two following ways. One is this 1 minus x square minus y square minus y square. Another way I can write it 1 minus 2 x square minus 2 y square plus x square. So, if this quantity is negative, then the entire thing is negative, and if this quantity is positive, the entire thing is positive. So, it means that this quantity is negative means x square plus y square is bigger than 1. So, then this quantity is negative, right. So, it means that 1 minus x square minus y square is positive. Now, this quantity is positive means this 2 times x square plus y square is less than 1, right. So, it means that if x square plus y square is greater than 1 by 2 and less than 1, then this x square plus y square is less than half, then it will remain this is. So, we can simply say that the x square plus y square is bigger than 1, then this will be negative thing, and if 2 times x square plus y square is less than 1, then it is always positive. But if we take this region x square plus y square which is less than 1 and greater than 1 by 2, then what should be the behavior here. So, we take our region bounded by these things, so circle of radius 1 by root 2 and 1. So, here this clearly 1 minus x square minus 2 y square is positive for x square plus y square less than 1 by 2 and negative for x square plus y square greater than 1. That is what we have pointed out here, that x square plus y square is less than 1, it is all positive, and negative for x square plus y square is bigger than 1. So, it follows that x square plus y square is increasing along any solution of 27 when x square plus y square is less than 1 by 2 and decreasing when x square plus y square is greater than 1. So, it means look at here, this is the inner circle and this is the outer circle. Now, this circle is correspond to radius 1 by root 2 and this circle is corresponding to the radius 1. So, if I take any solution here, right, if we take any solution here, then we know that your 1 minus x square minus 2 y square is negative here, because x square plus y square is bigger than 1. So, it means that your solution will try to, radius of the solution will try to decrease. It means that it will always come to say closer to the unit circle x square plus y square equal to 1. And if we take any solution here in a circle, then your 1 minus x square minus 2 y square is positive and your radius vector is trying to increase, and somehow it will try to close to your circle x square plus y square equal to 1 by 2. So, idea is that if we take any solution in this region which is bounded by x square plus y square less than 1 and 1 by 2. So, if you take any solution here, my claim is that that solution will remain there for this time, because if somehow this solution at some point it is trying to cross this region, then as soon as it crosses, then your x square plus y square is bigger than 1, right, and as soon as it is say on the say x square plus y square equal to 1, as soon as it try to move out of this region, then your dx by dr by dt will be negative and it will come to, it will force to be back to say circle inner to the circle here. So, it means that now there is another possibility that it will try to cross this inner circle and try to move to region there, but as soon as it is trying to cross this inner circle, then on this boundary of the inner circle your x square plus y square is less than 1 by 2 and hence your radius will be increasing. So, it means that when x square plus y square is less than 1 by 2, then x square plus y square is increasing. It means that radius will try to increase and it will force thrown in again inside your annulus region. So, it means that if a solution is started inside this annulus region, it will always remain there in this annulus region for all the future time t. So, it means that any solution is starting in the annulus remains there for all the time t, and also it has no equilibrium point, and hence because the only equilibrium point we can check that for this it is 0 0 here, right, you can check that it is 0 0 here. So, it means that this annulus region is not containing equilibrium point 0 comma 0, and hence this must exist a closed orbit on to which all the other solutions are spiraling inside this. So, it means that by Poincare-Bendixson theorem we can say that there exists at least one periodic solution lying entirely in this annulus. It is not telling which solution is your say periodic solution or which orbit is corresponding to periodic solution. It just tells you the existence of at least one periodic solution. We have seen in this particular example that with the help of Poincare-Bendixson we can say give and guarantee that there exists a one periodic solution lying entirely in this annulus region. So, here we can see that the Poincare-Bendixson theorems gives a guarantee of existence of non-trivial periodic solution, but it will not give any information how to find out that periodic solution, it just gives you existence. So, the how to find out the that exact which one is periodic solution and how to find out that periodic solution is not covered by Poincare-Bendixson theorem. So, here we will stop our lecture, and in next lecture we try to look at the possibility of finding the say periodic solutions orbit which is missing here. So, in next lecture we will continue the study here, and we try to focus on finding the orbit of the say periodic solution. So, that will discuss in next lecture. Thank you very much for listening this. Thank you.